let's talk about general components of AnyLogic. So to look at general processes AnyLogic, don't capture that. This is an ambitious agenda. I want to talk about stochastics. I want to talk about the uncertainties associated with running AnyLogic models, uncertainties over time, and how we can handle these in AnyLogic. This is one of AnyLogic's great strengths, actually. You look at it compared to something like recast. It makes it a lot easier than many other frameworks. And any other framework I know for agent-based modeling, certainly, for examining the consequences of uncertainty of time in your models. We'll see how that's done. We'll also look at sensitivity analysis. We'll also aspire to talk some about the model parameterization process and the model calibration process. Some of them may have to leak until tomorrow. Okay. All of these are very important conceptually and very important at a practical level. So we'll try to hit this in a way that allows you an appreciation for what's going on, but again, bears in mind the much larger volume of material I have on this step-by-step online right now that you can go back and go look at. Okay, so we're going to be looking at how AnyLogic handles stochastic processes. And the observation here is that all models, George Box once said, and Scott mentioned it yesterday, and this is one of the sort of chestnuts I'll trot out, George Box said, all models are wrong, but some models are useful. All models are approximate. They're like maps. So in a map, all maps are wrong. They're a simplification of reality. And what's really important is that different maps abstract away from certain details. So if you want to map a street map of Saskatoon, because you want to drive from one area of Saskatoon to the other, you'll want a map that hides certain details that you don't care about. Sewer lines, the presence of electrical connectivity, the slopes of the streets, and all those sorts of things. You don't need to know that. You need to know how to draw. One map will show you that. Is that map wrong? No, it's an approximation. It's an abstraction that captures the salient details for that problem, that question. Okay. How do I navigate through it? Another map, if you want to investigate the causes of blackouts within Saskatoon, you're going to need a quite different map. You're going to need a map associated with electrical connectivity, the electrical grid, to understand where the key points of failure are, and how the electricity is brought across the river, and ways in which it might be vulnerable to trees falling or what have you. And that map will be quite different. Similarly, a hydrological map to investigate causes of flooding, in cases of high rainfall. You want a map which has slopes, etc. These are all different maps. The only perfect map would be useless. It's the world itself. You can't carry that around in your car. So we build these abstractions, these things that leave out detail, are simplifications for particular purposes. And it's like that with models too. And you could say this model is wrong. Yes, it's circumscribed. Yes, it's an abstraction, but it may well. We hope that it will bring out the salient details required for us to rigorously reason about particular sub-areas. Just like a street map will allow you to rigorously draw how to draw through the city, even though it leaves out many salient details. Now, like all analogies, that analogy has its limits, but it is, I think, telling in certain of its features. So when we build these models, it's very common that we leave out certain features. But those features often will have some dynamics associated with them, some change over time associated. We leave out certain details considering the vagaries of people's mobility patterns, or considering factors such as rainfall, or the fluctuations of the economy, the stock market, which may have relevance to conditions of interest to you. Some of these things, like modeling climate fluctuations, modeling meteorological fluctuations year to year in the context of a warming climate. If you wanted to put in a whole model of that, it could be, it could be quite a challenge. And often we end up approximating many of these things in a stochastic way. So we end up approximating them as involving uncertainty over time in some sort of statistical model. What's considered stochastic will depend on the scope of the model. But generally, we start with a smaller model where more things are approximated. They're imposed exogenously, but not in a fixed sort of way, but in a stochastic way. So we will introduce stochastics in the model. But moreover, the basic mechanisms that we do simulate endogenously in the models, people's behavior, for example, as Alex has suggested, whether a particular person gets infected. Those things are quite directly stochastic within a model. So these transitions between states, for example, stochastic, there's a certain rate at which they occur. So there's a hazard rate, a chance per unit time of them occurring. And that's associated with an exponentially distributed time between infections, but the exact time or whether or not infection occurs before this agent dies and the country's competing risks. That's all stochastic. Whether, in a particular, you could run the model twice and get very different results. And AnyLogic supports this. It also supports implementing what's called a fixed random number seed, which means you run it twice and get exactly the same results. In other words, use precisely the same sequence of rolls of the dice as when you run it each time. But in general, by default, it's set to be a varying random number seed. So in other words, you run it 2, 3 times, 4 times, and you'll probably get a very similar trend out. But there'll be differences. There'll be differences in the vagaries of who happened to get infected before whom, and that sort of thing. So event firing, to whom a message is sent, the duration of some procedure that's undertaken. Generally, there's variations from simulation to simulation to simulation associated with these things. And when we compare model results, it's too bad Joanne's presentation earlier today didn't capture some of the more recent work, since some of those slides are put together. So she actually did very significant analysis at a statistical level of non-parametric statistical tests to understand which of those differences were statistically significant, for example, because of this variability. We want to make sure that our conclusions from the model are not simply the result of a fluke, that the one time we ran it was lucky in the sense that fewer people got infected in the intervention than with the baseline situation. We instead want to develop confidence that what we're seeing is statistically meaningful, seeing real signal, not just the vagaries of noise. So we typically approach this by running Monte Carlo ensembles of realizations. We run the model again and again and again and again. And we try to approach it in a statistical way, bearing in mind that we have no closed form statistical assumptions we can typically bring to bear on the distribution associated with a given model output, for example. So we make use of non-parametric statistics in approaching it. And often what you'll see is that the model results exhibit broad regularities, with really pronounced patterns. But then there's variation around those patterns. And sometimes it may not be purely local variation. It could be, 98% of the time the infection takes off, but 2% of the time it dies out, almost immediately. And you have this kind of bifurcation between these two very different extremes. In fact, very different sort of equilibria that result. So here, we're interested in summarizing variability. And as I said, AnyLogic actually makes this quite easy. So within AnyLogic, you can define, it provides a direct way to make use of Monte Carlo methods to draw samples repeatedly from distribution, to run a model over and over again. And moreover, it provides a way of accumulating data in a way that summarizes variability trajectory one over the other, but it's capturing density maps of the output. It's capturing two-dimensional histograms, or the 2D of time and value, in a way that will let you sort of recognize the spread or sort of level of dispersion among different outputs. So a key component of this is what's called the Monte Carlo 2D histogram, which you'll soon with which you'll soon acquaint yourself here. Within this construct, basically it divides up time into a set of user-specified number of intervals, and then you divide up the values. Maybe you're looking at prevalence of infection over time. So you divide up time into a set of intervals and prevalence of infection, maybe from 0 to 0.2, 20% of the population divided up into increments of 1%, 1%, 2%, 3%, etc. And these divisions define a uniform grid. And then AnyLogic will run your model many, many, many times and accumulate counts of the number of times the model falls in a given grid cell there. In other words, has at a given period of time a given range, it lies within a given range of value. Okay? So I'd like you to open up a model called SAR agent-based calibration. Okay? Now, the location of this model has sort of fluctuated in different versions of AnyLogic. So I'm going to just make sure that that you can locate it here. So I'll open it up here, and we're going to be using this model for the next few lectures. So it bears attention. My recollection is that it is yes, it's right here. So you just scroll down this set of models on the right-hand side. How did I get here, folks? I had AnyLogic and I did example models. This screen came up, and I scrolled down and looked at SAR agent-based calibration, okay? So I'm going to click on this. TAs, stand poised. Or sit poised. But, yeah. Who needs a TA? The TA stand ready. One deployment required in the back. Yes. Okay. Who else needs a TA? Okay. So Alex, help. Scroll down on the right-hand side, SAR agent-based calibration. Okay. So, ladies and gentlemen, let us open this model. So when we open this model, we see some familiar components, and we see some components that are unfamiliar. For example, some new types of experiment here. One with what appears to be a vortex, a maelstrom, and another which has a little picture on it. And so we're going to be learning from this model several features. I would note that while I start with this model here for simplicity's sake, I do build up model with some of these features, say for the parameter variation case, just so students can see how to build it up from the ground up. So if you're interested in doing that, you can refer to my online videos that demonstrate how to do that. Okay, so having opened that, I'd like you to double click on that last experiment, this Monte Carlo 2D histogram, okay? And you should see this sort of display, okay? So what we have here is at the top depiction of the experiment, and you'll notice this experiment is different from other experiments in several features. And one of the most notable ones is, ladies and gentlemen, this experiment runs the model more than once. Is it a TA? TA? Okay, two TAs are required in duplicate. So one in the back, one in the front. Okay, are we running short of TA power here? Okay, yes, we're, okay, the professor prepares for deployment if he has to. This particular scenario, this particular experiment is different in a couple respects. Most notably, it runs the model many times. So for the most part, we've been dealing with scenarios that run the model once. they're sort of almost coexistent with the main class. They run, they bring the main class into existence, they run some on, they show the result, and that's their life. Here, we have the experiment outliving the main class. It runs, it creates an instance of main, it runs it, and extracts values it needs, puts them up for display, and then runs it again. Like each time main is coming to existence, having values running, having values extracted, and being discarded. So it's running it many, many times, and we'll see that. But at the moment, what I'd like you to do is to, if you click on this whole experiment, you should see things like this in the general, I'll do it over here. So if you click here, you'll notice that down here, and I'll maximize this by double clicking on this tab. You should see something along these lines. So it's a parameter variations experiment. It has all these parameters that it knows about, and it allows us to actually specify a range over which they can vary. But in this case, we're just going to be running them with the same value over and over again. Now that may sound strange. Why would I run this model with parameters being the same value over and over again? Why would I do that? What's the motivation for that? Exactly. So there's going to be stochastics exhibited, which are going to mean that there's going to be variation between these things. So I'd like to run this, okay? So tell me how to run it, ladies and gentlemen. You've seen this many times, but tell me how to run this experiment. This is not a trick question. Please, a sanity check. Sorry? Thank you. Put me out of my misery. Sometimes you do a sanity check. Okay, and so here we're running. So I ran and I clicked this button. You'll notice that, again, this brings out that salient feature I noted earlier about how this is running many times. You'll notice that we have these simulations down here. It says run 32, 35, and this is an indication of my cores, how they're being used. My computer has two functional processors on it, two things that serve as processors, two cores associated with it, each of which can independently run this in parallel. And AnyLogic is using them to run successive versions of models, running up to 100. And you'll notice that this is the display of sort of the results of running this model many, many times. So, ladies and gentlemen, it's running more than 100. Probably because I frogged this model. How many is yours running? 200? Okay. Okay. So, we should prepare that by the list. But in any case, what we see here is the 2D histogram that I described a few minutes ago. So there's, can anyone interpret what's going on here based on what I said? What is this axis based on what I said earlier? This is actually time here. And here we're looking at the number of infectious individuals at a given time. So can anyone sort of characterize me here, so the coloration of the given bin indicates how many specific runs led. Let's consider a given bin here just after time 40. Here, let's consider this bin here. So what this is saying is there's a certain number of runs that in this time between 40 and something like 42.5, something like that, maybe it was 42, there were some number of runs where the number of infectious cases fell between something like, I'm guessing it's like 1,400 and 1,600. And for each of those runs, sort of increment to that bin. The darker one of these bins is, the more runs fell within that range. These things out here are white and indicate that there were actually no cases of this. Now, could anyone interpret for me? Incidentally, this graph doesn't really pick up the color variation right around this trajectory. Can anyone interpret for me visually sort of what's going on? Could you, if you had to summarize this for someone, what you were seeing, they were talking to you over the phone, what would you say is going on here? Remember, we've run this model many, many times, no parameter variation. What would you say the behavior of this model is? They said, oh, you know, what is that model telling you about the number of infectious cases that we should expect in the next few months? What would you say? Okay. So if they were to ask, well, is there a lot of variation you see? Like, is the model showing big bounds of variability? Is it showing any variability? Yeah. So for example, for the number of people infected between 40 and 42 days out, you know, there's some uncertainty whether it's going to lie. You know, it looks like between about 1,200 and about 2,000, something like that, with a peak here towards the center. We're going to see AnyLogic has two basic ways of displaying this. One is with sort of empirical fractals, although I'm not, maybe I shouldn't say that word. So it's sort of, one can sort of see envelopes that contain a certain fraction of the runs. The other is with bin counts. I believe this, what we're seeing here is bin counts. Okay, so you could say that, but am I missing something? If I said, you know, at time 40, you know, basically we're seeing between 1,200 and 2,000 cases, and where, you know, the largest, the most likely outcome being sort of on the upper level of that range, say from like 1,400 to like 1,800. What am I missing on? Yeah, so down here, there's a certain fraction of the time where basically there's no cases by that point. No cases. So you can see there. Can you see it on your screens? There's some small set of cases where down here there's no case at all. Now, no, this is darker down here. Why is that? You'll notice there's sort of a greater fraction here where this is sort of no cases. But what's going on here? Well, you have to remember that there's actually quite a number where it hasn't yet taken off here. And so some where there's kind of deferred or delayed sort of explosion in the number of cases. So a lot of these are, well, it hasn't yet taken off. Some of these here, for example, are some late bloomers, but also some cases where it's already died down, for example, where it's darker here. But it means greater number of runs fell in that bin. So yeah, that's right. So what this is saying is, you know, the first few weeks, the first 10 weeks, the first 8 weeks, or what have you, you're seeing very, very few cases. Now, if we wanted to, yes, Carlo.
So right around 20 on the
Yeah.
bottom of the x-axis.
Right.
Start to, like you said that some of them is taken off like that. Why don't we see any kind of upshift?
That's a very good question. And part of it is that what's being displayed here is actually so there's two levels of comment to this. Okay, would be my best guess. First of all, these bin colors are only distinguished to a certain degree. Some of this, what looks white, might actually have one or two sort of cases in it, and just being approximated, you know, sort of truncated to the nearest bin size, or to the next lowest bin size. And so if it doesn't make a minimum of 10, it may throw it blank. The other thing though is visually, what's shown on my computer is actually rather more textured than this. You can actually see some additional ones here that I can't see like visually on this projection. But let's go look at the data, because that's exactly what I was just going to go suggest. So ladies and gentlemen, if you go right click on this, and this is going to get us into an important issue that we'll be covering additionally. If you go right click on that and you call up, well, I've got cell running,
So I can just create a new Excel spreadsheet, or you could call it up there, and I can go export this data, okay? So here we have sort of the number of cases that, for a given interval of time, 0 to 2.5 days, fall within a given range of values, and you can actually look at sort of how many fell within that value. So Carmel, in this case, it's a very good question. What's going on there? We do have 32 cases here. This is that kind of darker case. Now, some of these individuals, there is sort of a leap here, and there's a leap up there, etc., where it may be shooting up in that sort of time, from this low value to up there. But to really investigate that more fully, I want to make time more granular. So in other words, make it more fine-grained to see if it's really going up. My guess is that this is a confluence of it rising on the one hand, and some that are coming down to this point and sort of being retained after that. But I would need to investigate that further. But I would start with this representation rather than the visual representation, which is just somewhat misleading. Okay, so that's a great question. Okay, so here we see some handling of these stochastic. Let's see. I have further discussion of this. I want to highlight the fact that this data is being accumulated in a construct known as a 2D histogram data. So if you go and you look underneath this experiment at what data structures are being used, in other words, storing this data, you look into analysis data. There's something called data infectious 2D, which is a histogram 2D data, and this allows you to define those horizontal intervals, in other words, intervals here over time, and the vertical intervals. And it also allows you to specify envelopes within which you may want to summarize data. Okay, there's two distinctions here we can make. So if you then go to the data structure that accumulates the data, okay, and we're going to come back to those sort of data structures in a bit for how we accumulate data within AnyLogic and how we export it, which is a very, very important practical consideration. So here you click on this, you can see these bins, and then that's the data structure that accumulates that, but there's a chart that actually displays that data. So it displays that data from the thing we've just been looking at, and you can summarize it either as bin counts or as envelopes, okay? To show it as envelopes, we get something more similar to kind of a box plot sort of thing. So particularly if you were associated with empirical fractals of like 25% on the bottom, 75% at the top, etc., we can get something sort of similar to an extended box plot for showing envelopes here, okay? So this is going to show this certain range, and the whiskers of the box plot are not going to be seen, but they could be deduced from the data. My own suggestion is this is great for rough and ready thing for kind of looking at the results. But if you really want to look at this, export it to R and use R as 2D histograms or use box plots on it or something like that. AnyLogic is pretty darn good for basic display, but if you really want to do serious statistics on it, or you want to do serious visualization, you're going to want to export it. And we use R a lot with stuff from AnyLogic. So here we can set the empirical fractals so that the envelopes such that they capture the median and some fraction around the median. So here these are the envelopes that are used to define, and we can analogize them to what we see here was the 25th percentile, the 75th percentile, and then the median in the middle. Okay, so you can go show bins, or you can do show envelopes. An example of show bins with a different model would bring out some of this texture. You see something like this, where it's not necessarily unimodal,
there's sometimes bimodal distributions, so a large number fall here, a large number fall here, a lesser number in the middle. This is from a different model, but you know, if we imagine slicing it at a point here, at a certain point in time, or a certain interval in time, what we could really do is we could create a histogram of the number that fall within different value ranges at that point in time. That's what the show hidden gives us. Whereas the show envelopes gives us something more similar to a box plot. It doesn't give us the histogram. It gives us something more like the location of these of different envelopes. In this case, it's 25% and 75%, sort of analogous to common box plot ones. Now, in the interest of time, I don't have time to go into some of the automatic throttling of Monte Carlo analyses, but suffice it to say that you know, if you want to, this is some basic statistical reasoning associated with this. If we want to divide the standard deviation of the sample mean here by a factor of 2, we need to take 4 times as many Monte Carlo samples, because the sample standard deviation for the mean is going to be decreasing by the square root of n there. There's also an option with AnyLogic, and I'll come back to explain this in a later lecture a little bit more. But suffice it to say that you can either say, I want a fixed number of applications. I'll come back to this issue later, but it turns out that that you can tell this thing, okay, I want to run this thing a certain fixed number of times, or I want to run this a certain number of times to achieve a level of statistical confidence in the results in terms of the value of the width of the distribution associated with the sample mean. And I have some slides on this in a lecture I'll be giving in just a few minutes, which help understand this some more. What I've tried to highlight here is just the broad strokes, the broad brush sort of depiction of these, how AnyLogic takes into account uncertainty in the model. I do want to bring out for you one aspect texture here, so you have some conceptual understanding of what's going on. Frankly, I feel really queasy showing you a pre-built model where you didn't build it yourself, because there's a fair bit going on. Ladies and gentlemen, if you are to go with this model and highlight this experiment, you'll notice there's actually some textured stuff going on in the advanced tab of this. And I want to help you understand how this magic is occurring. Like, how is it that it's running main multiple times and boop, it just gets the data to display in that 2D histogram? How does that happen? How does it magically suck this data out of from all these main experiments and just present it like that? Well, it turns out that there's clear mechanics for doing this. There's no mystery here. There's no magic here. It is straightforward if you know the basic mechanisms. And you'll find me talking about this in much greater length online if you're interested, particularly for the calibration lecture. But suffice it to say that in this experiment, there's an advanced tab. Associated with experiments. The advanced tab allows you to basically choreograph a set of activities to take place at different times during the experiment. We'll see this is heavily used here. It's heavily used in terms of variation, sensitivity analysis, and it's heavily used in calibration. Okay. So what this is saying is before each experiment run, it clears all the data. Before the experiment run, the run of all the runs, just starting this up before it's done any runs of the model. It clears all the data in this data in fact is 2D. That's this data that we exported to Excel. Clears all that away. Makes it all 0. And then after a given simulation run, after it's run this model once, we will then add in data obtained from main. So we run that simulation model in main. Remember, it's main that's running model here. Remember the main. And you run it out, and that a certain time, it's accumulated some data in main on the number of infectious cases for that run. We'll see that in just a second. And what we do is we take the data it's accumulated and we add it to this 2D histogram data set to sort of throw that in there saying, okay, this is where trajectories went for this run. And then we'll run it again. And we'll suck that data out of main and throw it in there. Why do we have to suck it out? Well, because main gets brought into existence, it's run, and it's going to disappear before we do the next one. So we have to take the data out of it. We suck it out like with a straw. And it gets sucked out, and it gets placed into this data structure here. And successive data is placed in there, and it's accumulating those statistics on each of those bins as to how many fell within this time range into this value range. And we keep on putting it in until we've run the model however many times. And at that point, we're done. And in the meantime, it's displaying it. So you'll notice here it says, so visually it said run 100 runs, but if we really click on this experiment, we'll see the truth of the matter. It's actually running 200 runs there. See that? So for each of those runs, it's just doing this. After it's finished running, it puts that data into this data structure that we saw earlier. This data where it's accumulating the bins, where it has a certain number of intervals from 0 to 2000, or to time, 200, sorry, etc. So this experiment, in contrast to previous experiments we've worked with, is run in the main class many, many times. Each of those times, the main class simulates the entire time frame, and then it takes that data out and accumulates it. And that's what we see visually accumulating as we run this experiment. Okay, that's what we saw sort of accumulating in this chart, and that's what we could later export. Okay, so people comfortable with that? Yes, question.
So the index for what we see here in the example shows that the number of articles is stuff. But opening with the example of what we did in class, there's no way that this is how many times the one is running.
Sorry? Oh, well, that's because this is a different type of experiment. So you'll notice that I had noted earlier when I opened this model, there's two types of experiments here that we hadn't previously seen. One of them, they're associated with different icons here. So this is the sort, this one that says simulation main. That's the sort of experiment we've been seeing. Okay, this one here. But in addition, this particular model has two different ones. One is one we still yet to come through the calibration. But the one that is shown here is called Monte, Carlo, 2D Histogram. That's a separate type of experiment. That's what's called a parameter variation experiment. You see it says parameter variation experiment. And it has this special mark, a tick, next to it. And that's a different ball of wax. It's a different kettle of fish. It's a different breed of cat. And that's something, if we want to add it to our model, we could do with file, new, experiment. And what we'll see is that there's a parameter variation experiment that we could add, okay? And that will allow us to build up something like this. Now, again, I have online videos which show how you build it up. So there's no mystery here, okay? Great question. Other questions? Yes?
In this model, if you give me certain parameters contact rate and certain value, these are fixed values. If
Yes.
you want to make them variable,
Yes.
is that possible?
It is, yeah, we can make them variable. What's very important, however, is that you not get confused by the terminology. So this is a great question. This question transcends this particular model, to be sure. So yes, I'm about to, yeah. So the question was, if we go to the main class here, remember this experiment we were just looking at, it serves to run main many times, right? It's running once, twice, 3 times, all the way up to 200, right? And for each of those runs, there's some assumptions that main needs to do its job. The assumptions are concerning the total population, the average illness duration, and so on. And right now, those assumptions are specified where? Well, they'll specify in the experiment we were running. It says in the general tab of that experiment, it says, okay, what values to use here. And what was noted is, quite rightly, that these values right now are all fixed. Could they be varying? Could you have parameters that change over time? And the answer is you certainly can. However, there's two cautions in order. The first caution has to do with terminology. That if you go look at one of these variables, for example, these parameters, what we'll see is that there's actually a thing that he says dynamic here. You might be fooled into thinking that that means, oh, I want this parameter to change over time, I'll make it dynamic. No, don't do that. Dynamic means something more advanced than that, and it's a very powerful thing. Indicating dynamic allows you to basically, at a conceptual level, allows you to pass in a function that does something in a way that hides a lot of the Java cruft with doing this. So it allows you to pass in, for example, maybe it's an intervention to undertake on each person in the population. So you could have different experiments that would intervene in different ways in the population. One, raises lowers the contact rate of the population. Another lowers improves hygiene and therefore lowers the chance per discordant contact that the infection will be transmitted. In other words, the chance per contact between a susceptible infect with the transmissional effect. Another one, speeds up recovery or something like that. You could pass those in as interventions from different experiments, and then each would just be applied to each person in the population before the simulation begins. So you can do that with a dynamic parameter, but a dynamic parameter is not used to just make it change over time. To make it change over time, you could, it's basically just functions as a variable. You could assign to it. You could, when you have a transition in your state chart, you could have someone's, for example, income change. So they acquire a job, and so their income changes. So up to get individual level. Here, you might have, for example, contact rate change over time according to a slider. Okay, so I could put in a slider that would slide and let me, during a simulation, it will allow me to change the assumption about the contact rate. Time is short. Maybe we'll do that. Yes, quick question. Yes, indeed. Yeah. Indeed. Yes. And I have that in my parameter variation talk that I'm going to give next. But AnyLogic doesn't currently support it, and they need to, and I told them that. And they need to add it. They should also support orthogonal array analysis. There's further some techniques drawn from dimensional analysis, which allows you to reduce the number of parameters you need to do it on, but still get the same information. So you can do it on 4 instead of 6, or 3 instead of 6, which can be very powerful. But at the least, they need to do left hypercube, because that allows you to really efficiently examine all possible values of discrete parameters over a wide range, and at the same time avoid doing an combinatorial exhaustive thing. Another thing would be very desirable is orthogonal array, which would allow you all pairs to examine, but not all possible combinations. So I think that should be straightforward, and I expect that fairly soon we'll support it. Yes.
Actually, it's funny. Like I said, when I worked with my job before, AnyLogic was working with SAIC within the graduate school and the OR department, and as you might imagine, that was orthogonal Latin algorithms, which are incredibly efficient. Like they take 26 design points and they compare up to 27 factors for 100 continuously varying levels of each factor, and that's just with 26 design points. That's ridiculous. But my point is that I've been beating the drum of that since I got hired up, we need better experimentation facilities in
Yeah.
that term, in those terms. But the thing is, I think that if you go to the C website for Memphis Graduate School, they have an Excel spreadsheet that will actually calculate it
Exactly.
for you, and you can read that into anyone.
Precisely.
So, I mean, it's a workaround, but you can do it. But I think we do need to.
Yeah, and similarly, there's orthogonal array things, at least that used to be online. You could get, I don't know with sureness that they're still there, but you could get it to print out a bunch, and then what you could do is here you could get it to when you in the general tab of the experiment, you could actually have it look up the parameter value for each successive iteration. Just look up what value to use, or what sets of values to use for each successive iteration. It would not be a hard thing to do. And Gerhard, if you were interested, I'd be glad to just let a TA work with you. They could produce a model which does this. We could add it to our example models if that were of strong interest. Yeah.
It's just on a similar line.
Yeah.
It's just if the research question works in retrospect, trying to identify the parameters that are not known,
Right.
known now.
Indeed.
So when you model it, then you know what the parameters are.
Yep.
And you draw that conclusion based on the similarity of the output.
Yeah. Right. Right. Yeah, and that's exactly, you've described to a T what we call calibration. Now, there's confusion about this because in different subcommunities of dynamic modelers, there's actually different terms for this process. In some quarters of the numerical analysis community, it's actually called parameter estimation. But we will be examining that exact process, and it's one that AnyLogic provides strong support for. Okay, so we'll be seeing that. But I'm going to try to weave in an answer to show a dynamically varying parameter with a slider a bit later. But because lunch is looming, I want to see if I can cover some material, and we'll see if we can come back to that, because this whole issue of how do I there's two sort of issues that are of relevance that I'd really like to make sure we cover. One is in response to the question, how do can I vary parameters? And I'd really like to show how you can do that with user interface components. So you can realize that you could add willy-nilly user interface. Willy-nilly is not a great word. It sounds like it's a matter of flippancy or something. It's done in a capricious fashion. But you can add to your heart's delight user interface components to AnyLogic models with typically they're quite straightforward to add. Not always, but they're quite straightforward to do the basics. And to change parameters, to change model variables, to interact with the model in various ways, to extract debugging information, to have it summarize model state, have an output. All these are things that you can do fairly readily. I'd like to show how to do that. The other thing is, I really need to show you folks how you accumulate information here, how you export it, that sort of stuff. And without that, this risks being eye candy. Was there a question? Question? No? Okay. Okay. So apologies for the brevity of this presentation.